Hi, I'm Doug Vogt from the Diehold Foundation, and this video is on what is light, what are the current theories of light and why they're wrong, and then finally, what is the real speed of light, which I think you'd be interested in. I'll be going through parts of Chapter 3 from God's Judgement and Chapter 2 from The Theory of Multidimensional Reality, both books you can get from Amazon or directly from the publisher. This is what we know of light. Incoherent light is white light, or light from the sun, a light bulb, whatever. Incoherent light goes into a prism. Because of the shape of the prism, it divides the different wave bands or wave frequencies of light into red to ultraviolet. This is the electromagnetic spectrum. It goes from radio waves, a microwave, IR, infrared. This is the only area that we can see. It's about 350 nanometers. It goes from 750 nanometers to 390 in the ultraviolet range. A nanometer is 1/1000th of a meter. Above that is high UV, then X-rays, and then what we think gamma rays on up. This is the current theory of what light is. It's part of the Standard Model, basically a quanta of light, which is basically a photon, hits a allegedly electron that's spinning around here, and it will raise its level to one orbit. You can call it an orbit. If it's a high energy value, let's say an ultraviolet light, it may go two orbits up. This is the current theories. And then it almost immediately gives up the energy by giving off a photon, either a low emitted or a high emitted photon. That's the current theory. And you're going to find out next why this is basically wrong. Here's some of the ways scientists have tried to explain the different levels of energy. One's a Lyman series, a Balmer series, and the Paschen series. This is what a real hydrogen atom actually looks like. This was done back in University of New York, Stony Brook. A guy named Stokes, George Stokes, who I knew, he's no longer with us. And you can see the center of the atom here, and these are the shells. Now this isn't hydrogen, this was something else. And the measurement here of A means angstrom unit. An angstrom unit is 1/10,000,000,000th of a meter, where a nanometer is only 1/1000,000,000th of a meter. You got that straight, you're doing great. This is a more current photograph of a hydrogen atom, and they list it as 256 ppm. Well, what's ppm? ppm is picometer. A picometer is 1/1000,000,000th of a meter. And that's what this is. The red in the center represents high electrical activity. And so this is where the atom, by my theory of multidimensional reality, it's a center modulation point. All the information that makes up the atom is directed there. And it in turn creates an electrostatic field around the atom, and that's what these shells are. By the way, because of the Heisenberg uncertainty principle, they know it's really not an electron as a particle zipping around there, because there's no way you can determine where its position is at any time. Those shells are very similar, or exactly similar, to the DE, F1, and F2 layers in our ionosphere. Remember from my video 1D, when I was talking about planets and a star, you have a center modulation point which produces a lot of energy, electrical energy, and it in turn creates electrostatic shells, which you could look at it as a group wave. Just like the shells around the atom, I believe, is like a group wave. This is where you have to put your thinking caps on and realize something's wrong with their model. This is, again, Kirilian photography, and this is the phantom leaf effect, where I explained what the phantom leaf effect is in video 1C. It's a high voltage, high frequency phenomena, and the leaf is photographed. After you cut it off, you have to take the picture immediately within 1, 2, or 3 seconds, no more, and then, or else the phantom disappears. But you can clearly see light being given off and the infrastructure of the leaf, but there's no matter there. So all that, what you've been taught, and I've been taught, that a photon is emitted from the electron shells from an atom, is wrong, because you've got light coming from no matter. But remember what I said, and the same thing here. This one's from a guy who I know in Brazil, and he took a very good picture of it, and you could see the electrostatic charge from no matter. So I'll explain in the center what's really going on. Here's another one, more recent picture I found on the internet, and you can see there's no leaf here. This is like the third photo he did. I did the whole series he's got in the other video, but this is not here. The matter's not here, but because of the high voltage, high frequency, it showed the conscious part of the leaf. It's still being broadcast to those coordinates in time and space. So the result is the voltage that is imparted to the leaf by the Kirilian photography, maybe 10 or 20,000 volts, basically permits the information that makes up the conscious part of the leaf, that other carrier wave, to show up in the form of light as well as electrical charge, because it had to develop the film. So this model is obviously wrong. There's no matter there in the other ones, but you still see light, as witnessed by the fact that it shows up on the photograph. After my first book, Reality Revealed, was done in 1977-78, a few years later I got a letter from a scientist in Tokyo, and this is the organization he was part of, and he was studying a Japanese student, a young fellow here, who was able to, it was like an Uri Geller. Uri Geller's reported that he could put pictures onto a camera by just his thoughts. This kid could do the same. So that professor, he built a device. This is one of his earlier ones with only one coil there. Basically a Polaroid camera modified. His later one, he had basically 9 coils connected to, this is like a lie detector test, tractor feed recording the electrical impulses from this experiment. And I'll show you some of the photographs. And remember, there's no light involved. Here's a picture of the latest one. The schematic is of this one. The film went here. Here's when you close it up. These are the connectors. And that's how he pulled the Polaroid film out. And there is he opening up the Polaroid film here. Here's one of his first tests, where the student did. He winds up putting JNA into the picture. Now he sent me a book. This is one of his books, and I'm going to show you it was 2 volumes out of this thing. They both were loaded with photographs and his experimentation. Did a good job. Here's a target photo, and here's his result. You can see these lights show up, but it's a slightly different perspective, and this kind of blends out. You don't know what the mind was trying to put together there. Here's the target photo, street scene in Japan, and here's the results of him putting the picture into the camera. The picture, I don't know who the person is, maybe it's somebody the kid knows, and he put it in the picture. Here's another, this is the target here, and telephone pole, street full of cars. Here's what he did with his mind. It's the same building, you could see that. No cars, a couple of people here. Here's the telephone pole. It's casting a long shadow, which is evening time. And this picture showed it sometime in evening time. It's a long shadow. Here's the kid sitting in the chair, and he throws a picture of himself sitting in the chair here. Again, there's no light. So where's the photons to expose the silver iodide? Where? It doesn't exist. This is an interesting one. Here's a picture of an office building in someplace in Japan. I'm assuming it's Tokyo. But the image he puts in the camera is above the building, outside up in the sky, which is kind of interesting thing. I put all four on here. It's just amazing what he did. He did it in black and white and did it in color. So his mind was above the ground, above the building, and through the projection. That's amazing to me. This I threw in just for good measure. This is UCLA experiment. You can get light actually from bubbles, from sound waves. Basically, the sound waves raises the level, the temperature in the cavitation of the bubbles so high it actually gives off light. I want to show you what the Japanese scientists did with the kid and what it looks like. This is the tractor feed stuff of what the kid did with his mind. So it wasn't just light he was putting in there, but he also created enough voltage that it was picked up by those coils. This is an interesting one. Look at those spikes. That's a lot of voltage. While he was putting the picture into the camera. The thing's loaded with a whole bunch of these, but the point is the consciousness is, if you remember what I said in video 1C, is a separate carrier wave. So by adding the voltage, his mind was, the kid is probably almost a fifth dimensional being. He's getting there. And he also, in his books, in the experiments, he also bent spoons like Geller did, and the same exact effect. Everything was the same. So what it says is that you've got two carrier waves, and that's important to remember. You got one that's the matter part of the leaf or anything else. Then you have the consciousness of a fourth dimensional being, or fifth, superimpose the same coordinates in time and space. And even that information can produce light and also electrons. Here's the classic, this is what the chemists use. Bless their hearts. This is astatine. Its atomic number is 85 and its weight is 210. And you'll understand why I'm showing this. This is their outline of all these electrons. Supposedly, every time an electron changes its energy state, it will give a photon or absorb a photon. Here's our wonderful gold. We all love that, don't we? Especially the politicians. Weight 197. So really close together. To show I really don't have much of a life, and over the last 40 or so years I've been in research, I have a book of all known at the time elements. It's a Russian book, copyrighted in 1970. And I have a huge database. And it totals, my database, 43,184 spectral lines from all the elements except one. Franconium, I think, wasn't discovered until after 70. But what was interesting to me, not just the spread, this is the number of spectral lines. Now, if you're trying to see this on a phone or a tablet, you probably won't be able to. You'll have to see it on a computer where they have a bigger screen. I do all my videos at 1920 by 1080. You should be able to see it. But the one that had the greatest spectral lines was iron at 4,169 spectral lines. In fact, it had 1,195 just in our visible spectrum. But what's interesting to me was this. Their theory about the spectrum was that where some of these had much less spectral lines, I'll give you, for instance, here's neptunium. Isn't that a funny name, neptunium? Its atomic number is 93, but 94 is plutonium. It has 754. Neptunium only has 115. And uranium, just next to it, 92, is 992 spectral lines. So why the difference? Again, copper, atomic number 29, 631, gallium only 100, krypton, number 36, is 891. So the question is, why this big difference between the number of spectral lines we see? Now, their excuse was, the accepted reason is that the outer shells of the electrons absorb the other spectrum in the atom. Well, if that was the case, then I guess krypton and this tungsten at 1020, they didn't get that memo. Or plutonium certainly didn't get that memo, and neither did uranium. So obviously their theory is wrong. The other part that was really interesting to me was only 7.37, about 7.4% of all the spectrum fell into the infrared range. About 33% was in our visible range, and that's only 350 nanometers. But about 60% was in that ultraviolet, really high up. So what I think is happening is the reason why astatine, we only have 2 spectral lines. I mean, that's ridiculous. And I'm sure, I think all of them have at least 1,000. If iron has 4,169, there's no guarantee we're seeing all of them, then they probably all do. They probably have at least that, maybe 5,000 spectral lines. I'm going to go back to this. This is important. One, I talk about Planck's time, and that's pretty important and fundamental for quantum mechanics. Either Planck's time is either 5.39 times 10 to the minus 44 seconds, and it's either measuring these 2 spikes or it's measuring these 2 spikes. This would be twice the distance. As I say that, if you remember my video 1C, this is a model, a graph of how the information comes into this dimension that creates our matter world. The spikes are similar to Planck's constant. It's basically our matter world. But there's no matter there, it's just information. This is the carrier wave. When the carrier wave crosses this x-axis, it bursts out like an envelope. It opens it up, and the thousands of spectral lines or information that makes up the atom pops out. It demodulates, creating, this could be a proton, and that could be the neutron. Proton, neutron, proton, as it goes through time. And remember what I said, time is nothing more than the rate at which the Diehold creates our information. The Diehold, if you're just hitting this video and not the earlier ones, is the name I give this computer. It's obviously a quantum computer that contains the information that creates our universe. So anyway, this is up for grabs. Now the scientists want to measure this. This would be a full 360 degrees. See, it goes like this to there, be 360 degrees. Now this would only be 180 degrees of it, from here to there. That's 180 degrees. The reason I mention it is because of what they call doublets, which I'll cover in a few minutes. Okay, what I think is happening, if Planck's time, whatever it turns out to be, is this way out here, 5.39 times 10 to the minus 44 seconds, that's really a tiny bit of time. I think these purple areas, what I'm saying is probably lower harmonics of the primary signal that's way up here. This may be one harmonic, this may be a lower harmonic, and finally get to this one. Here's our visible spectrum. Here's the high ultraviolet, which I told you 60% of it is there. I think with actinium, I think this purple area is like towards the edge of what we can perceive on the UV, and that's why we only see 2. Or the other one's like 100, and everything around it is like 700 or 800 or 600 or 900. But, this thing shifts depending on which element. And I think then it makes some sense of the spectral lines. Now, this is what the National Institute of Standards has all the elements there too. Now, he actually recorded more than what's in my book, but they record 452 spectral lines for gold. Now, this is supposedly at CERN, and basically it's a big round drum, and this is a tube, and the bullet goes in here, and they had a gold atom. They use either gold or lead. I've seen the same picture where it was labeled as lead, but it doesn't matter to me whether it's lead or gold. They're pretty close in atomic weight. This doesn't look like only 452 spectral lines. I mean, subatomic particles. Each one of those spectral lines represents a piece of information that makes up that atom. This looks like it's thousands, 4,000, 5,000 hit. I mean, this is not 400 and something. And the nuclear physicists are trying to make sense out of this. Good luck on that one. This is gold looking through the tube. Again, it looks like more than 450, doesn't it? This is lead. Now, what's interesting about this, what I like about the photo, lead's supposed to be 455 spectral lines of what the National Institute of Standards has. But notice the curve, after the impact, all the curves, most of these subatomic particles, in quotes, all have that semicircular curve, counterclockwise. And this is why. This goes back to video 1C. This line here represents that graph of the carrier wave. And every time it crosses the x-axis, which would be here and over there, it bursts out the information and creates that atom. So, but look, it has a toroidal path that's taking a curve. So what I think is happening is once they impart a kinetic energy so great that that atom can no longer exist in this dimension, all those different frequencies demodulate, but they still have that curve. By the way, the next video after this is on quantum mechanics or subatomic particles. Anyway, this is the classic visible spectrum from ultraviolet to infrared. Hydrogen, total 68 spectral lines, 5 are in our vision, in our 350 nanometers. Neon, 68, you can see, but there's less here. This is iron, 1195. Now, what was interesting, there's some that are 2 spectral lines very, very close together. Here's some more hydrogen, supposed to be 47. You can't see them because some of them are so faint. Oxygen, 143, but here it is. It gives you an idea. This is how we identify what elements are in any sample. You raise the level by voltage. This is taken from my Russian catalog. And this is gold, and this is the visible spectrum here. Now what I highlighted here, what was interesting, is I have 2 frequencies that are only 30.3 angstrom units, 10 billionth of a meter separated. Now this is the voltage they needed to see that, to see these things. That's what this represents. This is supposedly the shell, and this is a relative brightness. Some of the brightnesses on some of them are in the thousands. Literally, one I saw as high was like 10,000. Anyway, this is the meat and potatoes of the spectral lines of all the elements. This is what a gold atom really looks like. Now, this isn't 20 nanometers. It can't be, because these atoms, this is the outside shell. You're not looking at the nucleus of the gold atom in any way. They think is either 1.5 or 2 picometers. That's 1 trillionth, 1.52 trillionth of a meter. This, if this was right, would be like 67 angstrom units, which is way too big. This is most likely 1 to 3 angstrom units in diameter. No more than that. This is a further out picture of gold as it lines up. Okay, so show further I don't have much of a life, or that I'm just too curious. I did a table of sampling of carbon, silicon, iron, copper, gold, plutonium, and looked for, only in the visible spectrum, how many of these wavelengths were so close together they were less than the diameter of the atom. And with iron, I only did like the first page of it. Otherwise, I'd be still doing it. There's so many. Remember, it was over 1,100 spectral lines just in the visible, in our visible spectrum. But what was interesting to me was this is all angstrom units, which is again 10 billionth of a meter. The average for carbon was like 0.305 angstrom units, and that's like, they think the diameter of the nucleus is 0.152 angstrom units. So it's very, very close. The same thing here, it's about double here. By the way, I found at least 4 different tables trying to estimate the diameter of the nucleus of an atom. They're all different. they all range pretty much. It just, I don't think they know, and it's just a lot of it's guesswork. Plutonium, pretty big atom. It was 0.47. They think the diameter of the nucleus is 0.374 angstrom units. Gold they think is 2.75 angstrom units, and I get an average here. Oh, this is only 3 angstrom units. So it's very close. So the range. Okay, so what's really good? What are we really looking at here? By the way, I think this is the origin of why they think there is a positive and negative electron or photon. It goes back to this. As this carrier wave bursts into our reality to create the atoms, notice one could be a positive, one's a negative, or any way you want to look at it, but you have 2 different distances of about the diameter of the atom. Because remember, it's spinning around and creating this toroid shape. Here's the hydrogen atom again. This is where, look at this as a center modulation point. Not neutrons and protons. Like the graph shows, it's really the same information except one part of it's 180 degrees out of phase from the other. That may be why they didn't discover the neutron until, I think it was the 1920s. So anyway, it's again creating, you have information come in here, it creates voltage that creates this electrostatic field, which we call an electron. On the picture of the gold atoms, you're actually looking at the electron shell, not the nucleus of the atom. That's the electron shell. Here's more recent pictures. Xenon, 0.28 angstrom units, or it would be then 28 picometers. The red area shows high concentrations of electrons. In there is the nucleus. That's where this stuff's coming into existence. This is radon, same thing. This is Gaussian. I don't know who comes up with these names. Its atomic number is 118, so it's very, very heavy, 294. But what's interesting, they concluded from this that there wasn't really any shells. It was just the electrons went wherever they wanted, which is kind of what I'm saying, which really this is what this looks like, that it's like an electron cloud, an electrostatic cloud being created around a center modulation point. It was just like broadcasting. Now, the actual speed of light. Now, some of you from the graph may have already figured it out. But for the rest of you, this is it. This is the inside of a C-130. He's got his back door open. Maybe he likes to have a good view. And it's leaving a contrail. Now let's say this guy, this is a guy here, is saying, you know, I'm standing here next to my buddy, I'm not moving at all, I'm 0 miles an hour. But boy, that contrail is going at 400 miles an hour away from me. Isn't that amazing? But if we're on the ground and we see a jet going 500 miles an hour, we know this contrail is going at 0 miles an hour, and that's going at 500 miles an hour. So remember what I said what time was. Time is the rate at which the Diehold creates our information. The speed of light is 0. We're the thing that's being created at what we call the speed of light. That's the big difference. I don't know what this does to your formulas in quantum mechanics, your viewpoint, but you have to get the idea. In essence, this is a hologram, except this hologram creates what we think, what we call matter. Now, other scientists over the last 10 or so years are beginning to get the idea. In fact, one guy wrote a book, I won't plug his book, but he took it right from my first book, Reality Revealed, which is done 40 years ago. So, now you know. The light you see, in fact, humans give off light, but it's only because we're warm. So, we give off light too. If you raise the potential of iron when you're melting it and it starts giving off light, it's because the Diehold is sending more information down there to kind of stabilize it, and you see the light, the information. That light represents all those frequencies that make up that element, leaving it at the speed of light. That's the thing. It's like you have to turn everything upside down or invert it. But that's really what it is. Then you realize this is a created reality. It's basically a hologram. That's what we're in. And whether we like it or not. But that's the reason for I had to come up with this theory of the theory of multidimensional reality, that we exist in basically 3 different dimensions almost simultaneously. And I explained that in video 1C, so I'm not going to go over it now. Anyway, I did about a half hour, and I didn't want to go more than a half hour. But thank you for listening and watching. Diehold Foundation is a 501c3. It's a science foundation, not a religious one. Even though some of the work we do is somewhat religious subjects. But anyway, you want to contact us, info@dieholdfoundation.com. Thank you very much for watching.